Now for the third part, which is actually the most important. This is a continuation, you could say, to our considerations from the previous sheet, where we already found out that a so-called gradient vector field, look at this, this might be the gradient of a certain potential, and in this case, a possible potential function is even presented. If we can, and this is easy to show, if we can show that this vector field is the gradient of its potential, which, okay, or better speaking, if there is a valid potential to this vector field, then any path integral of this field along any path will be easily calculated by using the potential function. Not more exactly now, but more especially speaking, in any case where the path is a closed curve, I can easily predict that the result of the corresponding path integral of this vector field will be 0. So that's what we found out the previous time. But this time we want to just check it, do it, and just remember, please, we already proved that path P1 is a closed path. And if you want, we already proved that P2 is an open path. Just look at this little sketch again. If t equals pi over 2, inserting here, you can see cosine of pi half equals 0, while the sine of pi half equals 1. So we have 0 cubed, 1 cubed, times 4. So the point will be 0, 4. Okay, that's point B. So, sorry, 0, 4, yeah, that's right. So this curve P2 will start in point B and it will end in point A. It goes, in this case, clockwise along the curve, if you want, yeah, this way. It goes from B to A. It's an open curve, and it's allowed due to the, you could say, the multidimensional version of the fundamental theorem of analysis, of calculus. You can consider the potential function phi, if it's valid, to be the primitive function of the corresponding its own gradient. So I think that's what I coined last time. It's actually the case, you could say, that when solving a path integral, well, from, let's say, point A to point B of a vector field, which is the gradient of a potential, so I can replace it by gradient of phi of x along a path, then the result will be, I'm sorry, I don't have space right here. The result will be, you don't have to evaluate the path integral in this case. The result will simply be the primitive function, which is the potential of phi of x, evaluated at or between the starting point and the end point. If you don't understand this now, it's just think simply. I can replace this by, if it's a gradient field, by vector field f of x. You could really say that since f of x is the gradient of phi of x, so then phi is the primitive function of f vector. You could say a potential function is sort of the primitive function, the antiderivative function, spatially speaking, of a corresponding gradient field. Because its gradient is its first order spatial derivative. Okay, so this is almost the same, just higher dimensional version of saying, if I integrate, say, from x1 to x2, some function f of x over dx, we all know that if I find the corresponding primitive function, which is then called capital F, please don't mix it up, okay? So in this case, the capital is because F, like usually we have a force field and capital F is the symbol for force. So in this case, F is the derivative function, while phi is the primitive function. And in this case, the lowercase f is the derivative so the differentiated function, and the capital F stands for the primitive function. So that's just a question of symbolics. So don't be confused by that. But in the end, this is what you all know. We have to evaluate the primitive function from starting point, from starting value of x to the end value of x. So that's much the same thing we're doing here, but in a higher dimensional situation. That was my remark before we start doing so. Now, look, show that phi is a valid potential of f vector and calculate both path integrals as well along path p1 as along path p2. That's it. So, looking here, what do we get? Well, f of x equals gradient of phi of x, question mark. Here it is again. It's quite easy because you remember, and once we tried and well, the other way around, finding a potential for a given vector field, which was not, which was unknown. So if the potential is unknown, it's not so easy to find it. You have to integrate here over x, here over y, and possibly in 3 dimensions also something over z. In this case, we can just easily use the gradient from here to here. So that's what we do, right? We take the x, the partial x derivative of the potential, then we take the partial y derivative, and then we look, we just check whether these are identical to the first and second component of the vector field. If so, the vector field is the gradient of the potential phi, and then it's a gradient. It's not only a gradient field, it's also conservative. That's always the same situation, the same connection between potential and gradient field, and that's why I keep repeating it over and over again. So what do we get by taking the partial derivative of this term for x? Well, this one gets us 2x. That's easy. This one, since x is our variable, we, you know, what we do, we treat y to be, has to be a constant. So the factor of y cubed is there, and x is, well, differentiated away. So plus y cubed is the result. And here, this is an additive constant since y is treated to be a constant. And that's why it disappears when taking the partial x derivative. That's it. For the other part, phi index y, you know, partial derivative with respect to y, we get this one disappears because it's additively constant this time. This one gets differentiated for y, of course. X is treated to be a constant factor, stays there. But then y cubed differentiated gets 3 times y squared. So in the end, 3 times x times y squared plus next contribution, 3 times y, linear function of y, differentiated for y gets us plus 3. So look, these very different terms are exactly the components of the vector field. And now that's the proof, the valid proof, that f of x is the gradient of phi of x. And in other words, phi is the potential of f. So f vector field is conservative. It means that any closed path integral, in our case, it's path P1, which is closed, of this vector field along the path equals 0. We have a closed path, we have conservation, you could say, of energy in the physical, mechanical interpretation, and it means there's no result or the result is 0. Now, a little more interesting is path 2, because this is an open path. I'm not allowed to use this closed integral symbol. Anyway, as I told you, we can consider phi to be the primitive, in a spatial sense, as to be the primitive function of its gradient field, the vector field f. So that's why we checked that, we checked whether f is the gradient of phi and found out, yes, it is. So we may just insert to the potential. You remember this, or you know this all the time in electrical engineering. When you replace f for the electrical field, vector, and phi for the electrical potential, which is also called just phi, and differences of electrical potentials are called voltages. So that's it. Voltage is always the result when summing up, well, the effect of an electrical field along a path. You know, this famous probably you know this connection between electrical field strength, distance between two plates of a capacitor, right, and the corresponding voltage. Well, in English, it's called V. In German, we use U as a symbol, but you know what I mean. That's or in sometimes also this way, V equals E over D. This is the connection between these two entities inside a regular capacitor. You know what I'm talking about? Voltage between the two plates equals electrical field strength between the plates divided by the distance between the plates. So that's for the same reason as what we're doing here in the end. This is a very simple case because the electrical field is homogeneous inside the usual capacitor, right? So it's constant, locally constant. But in the end, that's much the same thing applied to electrical engineering. Well, anyway, you just have to insert to the potential function. Starting point is B, please remember, end point is A. It's the other way around from A to B. This time it's from B to A. That's because I was naming my points due to or referring to path 1. You remember? From A over B to C to D, A back to A. And then using P2, it goes the other direction from point B to point A. So that's correct, writing it down this way. We have to insert point A first into the potential, and then secondly, point B, and then we have to take the difference. Please help me. X and Y I may use for the positional vector. So X for the first, Y for the second coordinate. Look here. You remember that point A has coordinates 4, 0. Look again. It's here. It's on the x-axis. So 4 for X and 0 for Y. And then for point B, it's the other way around. 0 for X and 4 for Y. Back to here. I insert into this term. Here it is. So phi of point A will be 4 for X and 0 for Y. So we get 4 squared times 4 times 0 cubed plus 3 times 0. So no contribution here. Just here, 4 squared equals 16, remember? Minus potential at point B, which has coordinates 0 for X and 4 for Y. So we get 0 squared here plus 0 times something plus 3 times 4, which is 12. So in the end, we have 16 minus 12, which is positive 4. That's the result. That would be, for example, in an electrical setting, this would be, let's say, the voltage between these 2 points, like something like 4 volts between points B and A. And also this would be the result of a corresponding path integral of the electrical field along this path. So that's it for now.